Hi, I'm Mark Lepetis. I'm here with Bob Pack from GlobalFoundries, and today we're going to talk about the challenges in the Photomask shop and lithography.
My three friends here illustrate the wafer, the mask, and the OPC.
What happens when you have a failure in silicon?
It's not so easy. In the past, if you had a failure in silicon due to lithography, it was primarily a lithography issue. Now, it's an issue of not only lithography, but also mask and OPC. Yeah, so one of the problems is the MEF assumptions are overly optimistic. If we were to look at the ITRS roadmap at the mask CDU requirements, roughly 0.5, 0.9 nanometers, you look at the MEF, neighborhood of 4 to 8, you'd assume that maybe we're okay for 1 nanometer wafer lithography for CDU. But here's the reason why things are not okay. MEF traditionally assumes a global uniform isotropic variability error. This is optimistic. In fact, small mask features have poor mask process margin, inherently higher variability than larger mask features. So effectively, and I stress effectively, MEF can be larger for some of these critical structures. So the reason why small features have inherently poorer variability than larger features is primarily due to the dose slope. When you write a mask with an electron beam, variable shape beam mask writer, small features have a shallow dose slope and larger features have a more steep dose slope. So as you can see in this illustration, the smaller features may have, in this case, 0.67 nanometers per percent dose variability, whereas a large feature would have 0.53 nanometers per percent variability.
So which mask errors are really critical or matter?
Well, certainly, as we pointed out, small features have higher variability than large mask features, but that doesn't necessarily mean that all small features will result in lithographically poor performance. So for example, SRAF features, which are required for most technologies below 40, 20 nanometer technologies, will have very poor dose slope. But by doing simulations, you'll see that doesn't necessarily impact the main feature as much as you may think. So which mask errors matter? Just because a mask pattern has poor dose margin, it doesn't mean that it necessarily will impact the wafer. These are supportive features. These don't print. They're mainly used to improve the depth of focus. However, the only way you can determine whether they matter or not is through rigorous simulation. So in this case, for example, we take a test pattern array and we vary the size of the SRAFs to determine when a mask error such as that would have a significant impact. You'll see that below the design rule limit, the SRAF error impact on the main feature can be very significant. But above that, for this particular case, it doesn't seem to matter much. Now, one shouldn't rush to judgment and say this is always going to be the case. It depends upon your pattern at hand, so you must do rigorous simulation over the design rules of consequence.
Bob, tell us about variability and on the mask.
OPC mask designs can include many features that are intrinsically highly variable. This structure, for example, is referred to a dual offset aggressor case. You'll see that as a result of these pads on the opposite side of this main feature, the main feature is highly distorted, and as a result, the mask feature is very, very small. You'll see that the red regions indicate where the dose slope is very poor. The red, for example, indicates where there is a 1 nanometer per 1% dose variability. So in this region, you will have a much higher variability in your wafer lithography.
Tell us more about simulation and why that matters.
So simulation of masks has progressed dramatically over the past few years. We're now able to simulate an entire mask, mainly as a consequence of using advanced GPU technology. This simulation, which I'll explain, is done with the D2S TrueMask And you'll see that in comparison with the real mask, we have very good correspondence. So let me explain. In the top left-hand corner, you'll see a real SEM image showing the dual aggressor offset aggressor case. Now, when we simulate the exact same thing, we'll get essentially the same exact pattern. If we look at an Ames measurement, you'll see that comparing it to the simulation of the same structure, we get the same response. So we have very good correspondence between simulation and experiment.
What does that enable? More accuracy, better resolution?
Through simulation, we're able to see where regions of the mask have much poorer variability than other regions. And by that means, we're able to determine ways to mitigate that. We can, for example, add shots, so we can change dose of the shots to improve the dose margin. In this case, you'll see that a traditionally fractured layout has very poor dose margin in regions. In fact, the MEF also is 4.7. So this means that the high variability in this mask combined with the high mask air enhancement factor will result in very high wafer variability. What can we do to mitigate that? By using simulation, we're able to add shots and effectively reduce the MEF. So instead of 4.7, 3.0. And you'll see the dose slope is significantly improved. So you'll see that the benefit is in regions where you have high MEF, you're able to also find if it has high inherent mask variability. We can locally add features to improve the dose slope and thereby improve not only the mask variability, but the wafer variability in regions where it really matters. So there's some benefits to local application versus global. You may ask, why not just do this everywhere? Well, by doing it only where it's required, you're able to have a minimal impact on the mask write time. Remember, mask cost is directly related to mask write time, and mask write time is related to the number of shots that you're writing. So if we only add shots where we really need it, and we only add additional energy where we really need it, we have minimal impact on mask write time, and we minimally impact it thermally, and we don't have outgassing and other bad things. And importantly, we don't add to the backscattering.
So when we do simulation, what does that mean for write times?
Well, we're only adding shots, in this case, where we really need it. We're adding it where the MEF is very high and the mask variability is very high. High MEF and high mask variability is a recipe for catastrophic yield failure.
So you could apply this to post-OPC or the mask shop. In other words, it could be both or either or?
It could be either or, depending upon probably resources more so than anything else.
Now, would you use this in a obviously a complex mask in a multiple patterning setting, or is there what kinds of masks do you envision?
Any mask that has high MEF, that has high mask complexity, would be an ideal candidate for this. I think the industry is moving towards mask process correction and mask process enhancement. So mask process correction refers to doing essentially an OPC-like function over the whole mask to correct for E-beam proximity effects. In this case, this may be a component of or an addition to an MPC approach.
Where are we seeing the biggest problem as we're heading to the 14 nanometer mask, 10, 7?
Well, certainly you must consider the mask and the lithography in an integrated manner. The problems only get worse. The mask variability is generally considered that you must do mask process correction. The industry is determining exactly how that should be implemented, but this is one manner where we localize the mask process correction or mask process enhancement very locally through a minimal amount of effort, only where it's required.
Will we need this as we switch or migrate to, shall we say, inverse lithographic technology, or will we need to, or does this take place in the current environment, or as we move to pixelated masks or inverse lithography type structures, or?
Well, inverse lithography is just simply much more complex masks. And so if anything, this type of approach could be even more valuable for ILT. So I'd like to show what happens when you use the enhanced dose margin approach that we showed in the prior slide. So with a conventional mask, you'll see, and these are lithographic contours I should point out, you'll see that as we change the dose of the mask right, you'll see that you have a tremendous variation of the litho line width. A lot of pinching. It's very, very sensitive. With a dose-enhanced mask, you have far less variability.
What does that mean?
By adding extra E-beam dose energy in the small regions such as this, we have much less variability to any kind of variations in the mask process. That has the consequence of reducing your lithographic variability very significantly as compared to the conventional case.
Okay. Bob, thank you very much for some insight into some very complex but interesting information on the photomask and the directions. Thank you.
You're welcome.